Who's tired? Who needs another break? A break from their break. All right. Then you did it right. Congratulations. If you're tired, you did it right. Slightly recharged, I hope, but all right. So the first thing I want to say is that my philosophy about breaks is that it's like a wrinkle in time, and like, you know, school doesn't exist during that wrinkle, so now we're trying to crawl out of the wrinkle. And I didn't give you anything specific to do over the break. I hope you noticed. And I didn't do anything work-related over the break. I hope you didn't notice and won't notice. But the one thing I did notice this morning was like, oh, but jerky me did, you usually would have mind tap stuff for the chapter due last night on Sunday, and I thought I was so graciously giving you an extra day, making it due today. But that's not really fulfilling the wrinkle philosophy, is it? Because you got to do mind tap over 2 days. So I'm going to shift that to tomorrow. So mind tap that's due today is due tomorrow. So those of you that, apologies to those of you that like did it last night when it was still break. So my apologies. But anyway, I'll change that this afternoon. So that'll be due tomorrow. Okay, looking ahead, you have an extra. This is a little busy week coming back. You have a little extra assignment due Sunday night, next Sunday night. The I can do it or proof of ability assignment. Okay, it's a video assignment that you need to post. This is in preparation for your My Favorite Thing presentation due in a few weeks. All right, so if you haven't already done this or looked into this, just real briefly, what I expect you to do by Sunday is post a link, not a video, a link to a streaming video of anything. Okay, really anything. There's 5. It's a small stakes thing. There's 5 points associated with it. You'll get a point in no particular order if you submit something. If you submit a link, okay? Don't try to submit a video for this or the real video presentation. It needs to be a streaming video. You get that, right? I can't have 500 videos uploaded. Space, viruses, no way. Okay, so it needs to be a streaming thing, like a link to YouTube. Okay, YouTube's a wonderful, free place, easy place to put it. So give me a link. You'll get a point, okay? Even if it doesn't work or you don't fulfill the rest of the things, you'll get a point for doing something as opposed to nothing, okay? You'll get 1 point if it's, I'm trying to remember my 5 points here. You'll get a point if it's, if it works, if it's a streaming video, okay? You'll get a point if I can hear you. You'll get a point if I can see you. For this assignment, I do require you to appear in this video, all right? Flash it forward to the My Favorite Thing video. I actually don't require that you appear in the video. I hope you'll appear in the video. I think you'll agree with me when you're listening to, when you're watching a presentation, don't you prefer to see the individual giving it? Don't you hate those voiced over PowerPoints or something like that where, we're humans. We like to see who's talking to us. So I prefer, but don't require you to appear in that video. The reason I do require you to appear in this one is because if you choose not to appear later, I want it to be your choice and not because you didn't know how to appear in a video. So I want you to at least figure out how to appear in a video along with something else. All right? And it has to be some other reason to be watching it other than just you. You can't just open up your laptop or phone and just start talking to the camera. And that's also true for the real video, okay? There needs to be an oral communication component. You need to be saying something or singing something, okay? Some people sing, honest to God. I've had some people turn in like a rap, okay, or a song, or give a performance, or anyway, I'll get to that another time. But There needs to be an oral communication component, and there needs to be a visual communication component, all right? Some reason to be watching it, preferably watching you, but not just watching you, okay? So it can't just be you talking to the camera. You won't get full credit if it's just, you know, if you could close your eyes and get the same thing. There has to be some reason why someone's watching this, some visual component, all right? So I don't know if that covers all the points. If there's something to see, you're in the video, something that we can hear, and a streaming video, successful streaming video, and you just submitted something, okay? You didn't just turn in a blank, you know, there's no, okay? So small stakes, just 5 points towards your, you know, that like mind tap pile of points, okay? So it's small stakes. Don't skip it because it's small stakes and you don't know how to do it. This is a little short assignment for, especially for you if you've never done something like this, so that you don't naturally, like a lot of people, wait until kind of the last minute when you're doing your real presentation and realizing like, oh shit, this is more complicated than I realized. I don't know how to do this. For years, you know, I used to get those, and so I introduced this little, you know, intermediate assignment. Sadly, the people who don't do it are the ones that don't know how to do it. So don't be that person, okay? Now, for this week, for this video, it can be whatever. You know, we're not gonna, there's no other requirement about what it's about or how long it is, okay? If you wanna tell me about yourself or show me your pet or tell me a joke or just you can just pop it open and just say, look, here's some content and here's me, I know how to do this, thank you very much, bye. Okay, there's really no requirement for, it's just for your sake to make sure you know how to do this before it's time for the real video. Okay, any questions about that? How many have done that already and submitted? I know some people have. Okay, we'll get to that. By we, I mean me and my TAs who, you know, we got TAs coming. All right. So, chapter 9, stuff due tomorrow night instead of tonight. Video due by Sunday at the latest. So, because you got that on Sunday, I'm pushing that'll be chapter 10. I'll push that off till Monday, okay? So, kind of a thick week, right? So, tonight, tomorrow, Sunday, Monday. 3 things to do this week. Okay. All right. How many of you grew up with the Muppets? Come on, how many of you like, you know, all right. I hope you enjoyed that. So why did I play that song today? Because we're going to be focusing our attention on perceiving color in this chapter, all right? I want to remind you that something you learned in one of the first days of class, everything that we're talking about this chapter is an illusion, is like an earth illusion, okay? Earthlings, like us humans and other animals that we have studied that have nervous systems similar to ours and eyes similar to ours, which there are a lot of. So earthlings have this illusion of, not all of them, but many of them have the ability, like us, to perceive what we perceive as colors. We take that information, some physical information out there from electromagnetic energy, a little tiny piece of it, and we perceive colors. And so most of us can perceive like millions of different hues and shades of these colors. They're not out there, okay? They are not out there. Color is not a thing out here in real life. All right, we learned that early on. All right, for that matter, every sensation and perception that we have is just that. It's a nervous system perception. Okay, the sound of my voice is not out here. Okay, my voice is not a real thing out here. These speakers are wiggling air molecules that are wiggling your ears, and we'll learn all about that. And your earthling noggin perceives that as a sound, and a particular kind of sound, and a code that your nervous system learned how to decode into words and meaning, and that all is happening inside of your brain, and none of it's happening out here in real life. okay? Molecules of air are wiggling and nothing more. Does a tree make a sound if no one's there? You know, in the forest, if it falls, if no one's there to hear it? It doesn't make a sound if someone's there to hear it. It wiggles air molecules, and our earthling nervous systems perceive that as a sound and interpret it. And if we know what falling trees sound like, we know that code and we decode it and perceive it as a tree falling. So even when we're there, it's not making a sound. Okay, touch yourself. There's no such thing as touch. You perceive every sensation perception you have is happening inside your earthly noggin. Okay, so anyway, everything we're talking about today, or this chapter, is kind of illusory, but we're going to talk about it nonetheless because it's such a real experience for us. Okay, so here's a colorless photo. Well, just black, whites, and shades of gray. So real quick, what do you see there? All right, what is that figure in the foreground doing? I bet as an earthling, you're zooming in on that, this figure right here, as opposed to all the other figures. So this becomes, as we learned earlier, figure, and the rest of it is ground, including the literal ground and the trees. So foreground and background. Okay. So anyway, I bet you zoomed in on that. What is it? What is that object? How many of you see it as one object and then you perceived it as a second object? Okay? How many of you have seen this before? Have any of you seen this image before? It kind of made the rounds on the internet. It went kind of viral. All right? So, how many of you perceived it first as a guy, like maybe running or hiking or walking in the, about to like go into the woods? How many of you see it as a guy? How many of you still see it as a guy? Maybe wearing a backpack, his back facing you, black bushy hair, about to walk into the woods, all right? How many of you see it as something else? Okay. Tell those people around you what you see it as. What is it? Huh? Loud. Don't make me reveal it. A dog. Okay? And so that's really what it is. It looks like a guy, but it's a dog running towards you. Okay? That's his nose or her nose. Okay? Bushy tail, face, front leg, left front leg, back leg. Anyway, it's a dog running towards you. It's an ambiguous figure, and it's no doubt facilitated. This ambiguity is facilitated by a lack of color. Okay, there's just not quite enough information there for you to make it out. I don't have a color version of it to verify that, but I do have some others that'll give you this effect. Okay, so one of the reasons why we have color vision, men, don't ever forget that reason you've got a brain in the first place, a nervous system in the first place, evolutionarily speaking, was to be able to move, all right? So you're not implanted in the bottom of the ocean, okay? We started to move. We eventually moved out of the oceans, and we, became all kinds of life forms on land, and we move, all right? If you don't move, you immediately kind of lose your nervous system, all right? or a big portion of it. And then we have the sensate, we have senses, particularly vision, as a way to help us move so that we can move better. We can move towards and away from things and avoid things and find things and so on. All right? Well, color, the ability to perceive color evolved because there's useful information in color, okay? So, if your survival, if you were hungry in the woods, would you be able to find what to eat here? Okay? It'd be a heck of a lot easier if you saw it in real, so-called real colors, okay? So watch that again. It was pretty cool, all right? You absolutely can't see berries until you can see the color of the berries, okay? All right. Now again, don't forget, the berries are not red. The leaves are not green, okay? If anything, the leaves are everything but green. The berries are everything but red. As we're going to learn, electromagnetic energy of this particular waveform selectively gets absorbed and reflected by the things it hits and lands on. So the green leaves are essentially absorbing all of the wavelengths except the ones we call green. and green is bouncing off of it. So it's really everything but green. The berries are everything but red. Red is everything, every other wavelength, the other wavelengths are more selectively being absorbed by the berries. And I don't quite understand that. I got light reflecting on, bouncing. So I'm absorbing light. That seems kind of weird, okay? Am I getting heavier by all this light? I'm absorbing energy that I don't see. I don't know. And anyway, the leaves absorb some of that energy, and they're able to do something with it. They can make energy. I don't know how to. My body didn't evolve to know. It doesn't use that energy to make energy. But anyway, okay. So anyway, our survival depends on seeing color, including like back to this image. If this was like something scarier maybe than a dog. If that was a bear and you're sitting there going, oh, look at that guy running into the woods away from me, but it's really a bear running towards you, that would be maybe a little bit disadvantageous, okay? So, speaking of bears in the woods, how many of you can see the bear in the woods here? These images are from your book, so by the way, you've seen these before. So anyway, I've just blended them together here, so let's add the color back to that image, and oh, there's the not very scary looking bear, but there's a bear, okay? So it would not really be, even if that's, I don't know, even if it doesn't look scary, maybe that's a baby cub bear or something like that, but mama bear, papa bear might be right next to it or behind you, okay? Not a good place to be in real life. Okay, so color signals are gonna have a definite evolved advantage for, the nervous systems that have evolved to incorporate this form of energy into a perception, okay? One rather trivial function it serves is it just makes it, once we learn colors, when we learn what colors things are supposed to be, we can see them in the first place, we can identify them, and we can do all that faster, all right? So, if you show people images of correctly colored objects and incorrectly colored objects and just, maybe flash them real briefly or whatever, give them a reaction time test, people will more rapidly identify them and more correctly identify them if they're the correct colors. All right, so we have to know a thing or two about about light and color before we can proceed. So probably the smartest nervous system ever to have evolved is arguably Isaac Newton. Oops, not that Isaac Newton. This Isaac Newton, okay? A lot of people credit him as being the smartest human to have ever existed so far. His contributions really are staggering, and especially when you consider the age at which he made them. By the time he was your age, he had already proposed, he'd already come up with calculus and principles of light and gravity, and just the contributions that he made are just absolutely staggering. Some of them have been modified and added to and, made better, okay, with new information, but just given the fact that he was not as high on shoulders of giants as they say, as, we're on the shoulders of this giant, okay? So anyway, one of the, his contribution that we're gonna literally focus on today is his ideas about color and light, okay? So he was the first to sort of identify and, correctly propose that what we call white light was really made up of a infinite mixture of other colors, all right? And so he did this by making observations of light passing through different kinds of lenses, including prisms. And you've probably experienced this, with prisms or other, cut pieces of crystal or something. We sometimes hang these in windows and things like that, and they, light shines through them and it casts rainbows, okay? So we see, we see the colors. These things, serve to split that white light into its color scheme, all right? And again, it's like a quirky perception that we've evolved to do. These colors are not there. The wavelengths are, and so he talked about this energy being a wavelength. And we've since modified that, and we now, physicists talk about light being both a wave and simultaneously a particle, which, and they're not just saying, hey, we're not sure which one it is. It's both somehow, and I don't wrap my head around that because I'm not smart enough. I incorrectly think of it as a photon wiggling, but it's not, okay? Photons don't wiggle, they travel in straight lines. So as a thing, it's a photon zipping along in a straight line, but yet it's somehow also a wave, all right? I can't do that, okay? So anyway, the prism splits these wavelengths into different measurable wavelengths. So we can measure the wavelengths. We've developed things, machines that can measure the wavelengths, and we give them numbers and talk about the certain number of nanometers wide that the wavelength is. And then we associate them with our made up perception of colors. So if they wiggle more slowly, they look dark and blue, and if they wiggle medium lengths, in this range of numbers, we label them as green through yellow and orange, and then red, and then onto purple, and so on. Okay, so we give them different numbers, right? And so there's a reality there. So since we've developed devices that can quantify this, and we can, it matches our perception as well, and these machines can say what wavelength a beam of light is, all right? And then our brain does something magic and labels it, puts a color associated with it, okay? But a photon wiggling at whatever a photon does that makes it, if wavelength is 600 nanometers, and similar nervous systems are likely to perceive that as like an orangish color, okay? All right? If it's wiggling along at this wavelength, we'll call it green and so on. So there's that, all right? So, Newton was the first one to propose that. So anyway, so light hits, these wavelengths hit objects, and I just mentioned a moment ago, there's the chemical properties of the things it hit causes, some of it gets selectively reflected and some of it gets selectively absorbed. All right? So I don't really understand that, but I'm looking around and I see what look like red chairs and black chairs, and some photons are being absorbed by both, but the ones that look red to me are more selectively absorbing wavelengths except the red ones. And the red ones are bouncing off of it for some magic reason. Something about the chemical in the fibers on that chair is selectively bouncing off more red, and the one next to it is not. It's absorbing the reds more, okay? In fact, it's absorbing many more of the wavelengths, and therefore less is coming back out, and it appears to be black. So things that are black is not a color, it is not a wavelength. Look at back on the, it looks dark, but there's no black light. There's no black wavelength. Black is our perception of the absence of wavelengths, the relative absence of wavelengths, all right? And I had a whole thing about that with the projector, okay? So anything that you're perceiving as black, like the text is in black ink, and light is beaming onto that thing, but the projector is not beaming lights where those words are, all right? So it's selectively bouncing off less, and that white screen is not bouncing off as many of wavelengths, and your mixed up noggin perceives that whiteness as black. Boom. That's fucking weird. That's really weird. And it's inarguable. It is inarguably weird. That black text up there is actually white, okay? There is less light falling on it, but it's a white frickin' screen, and your brain sees it as jet black. Okay. All right, that's so that's selective reflection and absorption. Some things are, so-called transparent, or at least semi-transparent, like some liquids, like water, or glass and plastics and all kinds. We got things that are, clear, semi-clear. And so some light waves can pass through them, but some mysteriously get absorbed. So there's some selective transmission through and absorption by the object or the fluid, okay? So we wind up with what we can call transmission curves, which plot the percentage of wavelengths that get absorbed and either reflected or passing through, all right? By the way, there's, what we've been calling, all of this is referring to that tiniest sliver way back when I told you about, like, electromagnetic energy is everything from, I don't know where we got gamma rays and X-rays and microwaves and radio waves and all these different, wavelengths on either side of the spectrum of what we call white light. That, again, remember, that's the tiniest little sliver of electromagnetic energy possibilities, all right? So the other ones we don't see, we don't have an apparatus that gets, that anything happens when it gets struck by them, okay? Our body is struck by all kinds, you got radio waves passing through, you got X-rays passing, you got, there's sunlight that's just beaming right through this building, right through you, right through fucking Earth, right out the other side, okay? Explain that to me, okay? And then some of it's getting bounced off by the atmosphere. We're not getting fried completely because this weird atmosphere, this tiny little film of atmosphere is bouncing off like ultraviolet light and all kinds of, really dangerous ones that would just burn us to a crisp, okay? And then other ones are just passing right through us, okay? So it's deep. So anyway, we're talking about the tiniest little sliver. All right? So these things form, curves, transmission curves that we can plot, that we can talk about, and we can share our experience of what we perceive when we see them, okay? And again, wavelengths in this neighborhood, on this, this object, if we were holding it and it was sitting in front of us, it would be absorbing and reflecting certain wavelengths, and a bunch of green wavelengths would be bouncing off of it, and it would help us identify it correctly as a ball of lettuce, all right? And this one is, a ball of tomato, okay? Selectively bouncing off more of these in the 600 to 700 wavelength range, and these other wavelengths are getting absorbed by the tomato and becoming the tomato. All right? So those are what we call, chromatic colors in this, rainbow scheme. There are also colors that we call achromatic, and these get a little bit weird. Some of them are, kind of normal sounding, like white, gray, black, are really, they're not colors. They're achromatic. They're, not chromatic. But I don't have any examples up here, but other chromatic colors are, like metallics, okay? Can't find anything metallic. When you look at, jewelry, when you look at silver, gold, when you look at metals, they're, what color is, gold is a color, but, right, you can't, I can't project really accurate gold. I can't, anyway, it's an achromatic color, all right? I'm going to talk about there's a other fun achromatic colors that we do talk about all the time, like pink. I see a pink sweatshirt. That's just beautiful right there. Okay, I'm going to talk about your pink sweatshirt. It's a wonderful color. Okay, but it's not one of their chromatic colors. Pink is not in our rainbow. Pink is just red with a bunch of white. An achromatic amount, it's a high blend of achromatic whiteness and a little bit of, the more red it is, the darker the pink, the less red, the more white. The more the pink. Anyway, pink is an achromatic color. We're going to learn about another achromatic color that's kind of more similar to your sweater. Your sweater is, I'm going to call it magenta. As you're going to see, probably not today, but next time, magenta, that's not a color. Magenta's a fake color. All colors, quite honestly, are fake. That's my whole theme here today, okay? But magenta, which I'm not saying your sweater doesn't exist, but that color magenta doesn't exist. There is no wavelength associated with magenta, okay? So, yet we undeniably see the color magenta, and as we're going to learn later, it's like, that one's a real neat trick of the nervous system. The nervous system just sees wavelengths that, I'll give you a little preview. They should be green, but we've got green receptors. You've got green cones that wiggle. They're not colored green, but they really get happy when green wavelengths in this neighborhood, when those wavelengths hit, about a third of your cones, those cones are like, that's what we do, okay? And so as we're going to see, magenta should be a blend that looks like green, but it's not green. So your brain says, I'm going to make up a color. I'm going to call it magenta. Okay? You're going to see that soon. Makes up a color. Okay, so anyway, you're just starting to get this idea that there's different wavelengths. We categorize them into just three. We got to be simple. Humans are dumb, so we just take, bazillion wavelengths. We call them short, medium, long. Okay, we categorize them in those three categories. Because we've discovered, thanks to Newton and discovery since, that we've got three sets of cones. One of them I just mentioned that respond best to these, short wavelengths, medium wavelengths, and long wavelengths. Okay, so that short wavelengths correspond to the bluish, hues, medium to the greens and yellows, and the long wavelengths are seen as red. And if we see all of them, if all three of them are wiggling equally, we see it as white. So you see the background of this slide. This one's less of a trick, okay? Because that is again a white screen, but it looks whiter. You can see the edges of that white screen, and they look gray. It looks gray, okay? So that white screen sometimes looks black, sometimes it looks blue, sometimes it looks gray. And then, the parts of it that are white, getting all three wavelengths, short, medium, and long, blasted on it. And so your brain perceives that as whiter than white, okay? Okay, if all three firing, banging away, all three of your cones are firing equally, your brain perceives that as white. Again, achromatic color. It sees it as white light, okay? The absence, if we turn off all of the lights in the room and close it up, airtight, light tight in here, it'll just be no wavelengths bouncing around and we'll see blackness, okay? So, all right, here's a little bit more about that.
Colors are all around us. They seem simple, but they're actually the result of a complex interplay between physics and biology. But what are they, and how do we see them? Color is the way our eyes and brains perceive light. Light is a wave, and like any type of wave, every light wave has a particular wavelength, the length of each cycle of the wave. There are many different wavelengths of light, but we can only see light in this little range of wavelengths, called visible light. Everything else is invisible to us. The sun is constantly emitting basically every wavelength of light. All those wavelengths are shining on this car. The car is made of a material that absorbs most wavelengths of visible light, but there's one wavelength of visible light that it reflects. Some of that reflected light goes into your eye. Your eye tells your brain about the light, and your brain uses that information to make you have a particular perception of color. The color we see is based on the wavelength of a light. Red is how we see the longest wavelengths of visible light. Then there's orange, yellow, and so on. The wavelengths of visible light form the colors of the rainbow. Also, the more light there is, the brighter the color we see, and the less light there is, the darker the color. This gives us multiple shades of all the rainbow colors. But there are more colors than these. What about white, and pink, and brown? Well, it turns out that most colors are more complicated than just one wavelength. Most colors are a combination of multiple wavelengths. Specifically, we can say a color is a certain amount of each wavelength. For example, you see pink whenever a lot of red light plus a little bit of every other wavelength enters your eye. Brown is a medium amount of red light, less orange, less yellow, and none of any other wavelength. White is simply a lot of every wavelength, and black is none of any wavelength. But how do we see these colors? Well, when light enters your eye, it hits your retina, where there are light-sensitive rod cells and cone cells. Only the cones are used for color vision, so we're just going to focus on them. There are 3 types of cones, and each type is sensitive to different wavelengths in different amounts. There are the L, M, and S cones, most sensitive to long, medium, and short wavelength light, respectively. Each type of cone reacts a different amount to different wavelengths. Let's look at L cones first. They start getting sensitive around here with very low wavelength red light. Then, as the wavelength gets shorter and shorter, L cones get more and more sensitive, eventually peaking in sensitivity at around yellow. Then the sensitivity drops back down again. L cones aren't sensitive to blue light. Finally, there's another little bump of sensitivity to violet. What all this means is that yellow light, for example, makes L cones react a lot. Green light makes them react a little bit, and blue light doesn't make them react at all. The sensitivity graphs for the other types of cones are just simple peak-shaped curves, with the M cones most sensitive to green light and the S cones to blue. Let's see how the cones react when pure red light comes into your eye. The L cones are moderately sensitive to this wavelength, so they sense a good amount of light. The M cones aren't sensitive to this wavelength, so they don't sense any light, and same for the S cones. Your brain takes in this information, and based on it, it makes you have the sensation called red. How about white? Well, since white is a lot of every wavelength, it impacts all of your cones a lot. Based on these responses, your brain makes you see white. And for pink, the L cone reacts a lot to the combination of the large amount of red light and the little bit of everything else, while that little bit of everything else makes the other cones react a bit too. These responses make your brain give you the sensation of pink. The color sensation that we have is based entirely on the cone's reactions to the light. What this means is that if different combinations of light make the cones react in the same way, we'll see the same colors even though the light is different. Let's look at white, for example. We see white whenever all the cones react a lot. As we saw, we could create that reaction with a lot of every wavelength of light. But we could prompt the exact same reaction with just 3 wavelengths. The L cones react strongly to the yellow light, the M cones to the green, and the S cones to the blue. This is the combination of reactions that makes you see white. What this means is that if this combination of just 3 wavelengths enters your eye, you see exactly the same thing as if every wavelength entered your eye. In fact, for any color, there are multiple combinations of light that make us see that color. For example, this makes us see orange, but so does this. So a color is not just a single wavelength of light, and it's not even a combination of multiple wavelengths of light. Really, color is our perception of light, created when light from an object enters our eye, our cones react to it, and our brain gives us a certain sensation of color.
All right. Okay, that was everything I said. I got a trick question for you. What color is the sun? If you were going to paint me a picture that included the sun up there in a circle, what color would you draw it or paint it? Which crayon would you get out of your box?
Yellow.
Yellow. And it's always yellow, right? The sun is yellow, okay? The sun has all of the wavelengths that we just been talking about, okay? So sunlight is, so-called white light, meaning the sun is white, people. The sun is white, okay? You need to be an astronaut and have been up there. Once you get out of our atmosphere, you will, I haven't done it, I haven't seen it myself, but they tell me it's white. And I know logically it's white because we call what we see white light. It is white, okay? To us, to our noggins, we perceive it as white because we have these 3 cones that get really excited when that sunlight. Now, so my point here is the sun is beaming all of these wavelengths, including a bajillion others that we don't see, okay? It's emitting all of those wavelengths, okay? We have things like these lights, like the projector lights. The projectors has LEDs that emit red, blue, and green only, what we call red, blue, and green, so 3 wavelengths. compared to the sun's almost infinite wavelengths, okay? So real sunlight is emitting, a bazillion different wavelengths, okay? All of the other light fixtures that we have, and we've got whole bunches now, makes your head hurt when you got to pick out a light bulb. You get it home and you put it in, it's like, I don't like this color of light, okay? So anyway, they used to be light bulbs and they were always yellow, okay? Now we got, anyway, all of the light bulbs that we make are not, they're not sunlight. And so they're, and to the extreme, all of these devices you're all staring into and being projected on, red, blue, green, red, blue, green, red, blue, green. That's all they can, that's all. And that, that's not a coincidence because they match the red, blue, green sensitive cones we have. So our cones are, we don't have an infinite number of receptors for all of the individual sunlight wavelengths in that narrow spectrum, okay? We only need 3. We only need 3 specializations to get enough information out of it, okay? We get we can perceive, millions of different hues. Now, some people have a 4th set of cones. More likely to be female. I don't remember the percentage of people who have a 4th cone, but so they got a 4th option there to add more information to the brain, and they can see more than the millions of colors that we do. They can, if you wonder what that's like, I mean, when you look at those spectrums of colors and you can see different hues of reds and greens and everything, they can just see more hues. They start to blend together, and we can't, the rest of us with just 3 can only see a few million. Okay, they can see, significantly more, okay? So that's kind of the difference between sunlight and all the other kinds of lights that we humans have created. We're taking advantage of the fact that we've got most of us have 3 cones that can selectively get diddled by those light fixtures and see things in reasonably close proximity to sunlight versions of colors. Trying to go to the next slide.
Colors are...
Okay, so with a few minutes left, I'm going to start to get into complicated things here. So right now, we've been talking about sunlight, artificial lights, okay? But we also have pigments on things, like our clothing, like our chairs, like our objects have pigments. And pigments blend together different than light does. So this can get a little bit confusing. There's things that overlap and then things that are different. So we have to talk about color mixing. And when we do so, we have to keep in mind whether we're talking about the pigment on the objects or the light that's being absorbed and reflecting off of those objects with their pigments, okay? So we're going to talk about additive color mixing and subtractive color mixing, all right? So, and it's different for lights and for paints and pigments, all right? So, we've been talking a lot about light, so this all feels familiar to us now. So, we haven't yet talked a heck of a lot about, how they blend, but a little bit. We've had some examples, but this device has, again, red, blue, and green lights in it, and all 3 of them can create a really nice white, a white that closely matches if we were out in true sunlight with its white light falling, with all of those wavelengths falling on the objects, okay? But it turns out that these rods and cones are really quite adept in that, we really only need 2 of them to produce some color blends, including white. So if I shine just the blue light in there, the blue lights, LEDs, and just the yellow LEDs, and keep the red ones off, okay? The blue ones will, if they're beamed separately, will look blue. The yellow ones will look yellow. But where they overlap will produce white, okay? So it won't be as good a white as if the red one was also shining, like over here. This mimics, all three of them on. So anyway, any two of them can give us different blends, and two of them can give us white through other, like blue and green give us this cyan color, blue and red give us this sort of purplish, this fake magenta color, which we'll get to. And green and red produce, mysteriously enough, yellow. That's the blend, to me, that is the weirdest one. I don't know. That green and red, that's just me maybe, but green and red produce yellow. And then all three of them will produce white. But anyway, any two of these can also produce some experience of, not any two of them, anyway, I'll get to that another time. Okay, so anyway, you have to compare that with pigments and paints now and the objects, stuff out, the things that out on stuff. All right, so like we've been saying, some things get absorbed and some wavelengths bounce off. So something that's got a blue pigment, blue paint, will selectively absorb the reds. It'll and it'll bounce off some of the greens and a lot of the blues. Okay. All right, and we'll perceive that pigment as having blueness, all right? Again, there's nothing blue in the paint, all right? The blue paint doesn't exist. It's our perception that we'll see it as blue, okay? Yellow is selectively bouncing off a lot of reds and a lot of greens, and it's absorbing the blues, okay? And so on. So if you mix blue and green paint together, you'll get green, okay? Which is different. Now, if you're paying attention, blue plus yellow paint gives green, but blue plus yellow light gives you white. So that's your first little, like, hey, wait, something's different between pigments and lights, okay? There's a difference, okay? So when you add different light wavelengths, they add up. We call that additive light mixing. When you add pigments together, it's a subtractive process because all pigments are absorbing some light. To see the pigment, you have to shine light on it. You know that. You can't see pigment. You can't see paint in the pure darkness. Okay, so pigments rely on color reflecting off of them, and so when you add more paints together, each paint is absorbing some amount of wavelengths. The more that you're adding together, the less light is able to bounce off. So how do you make black paint? Just keep adding colors. Okay, take red, blue, and green paint and add them together, and you'll get a very brownish, you'll get a blackish color. All right. Add lights together, add them together, it gets the opposite. They get brighter and whiter. Okay. Black is the absence of light, except in paint. Add paints together, and you get black. It's an additive process. All right. There will be more on that on Wednesday when I see you next. So that's perfectly timed.
At Zeeler, we partner with...
More Muppets on Wednesday when I see you. Enjoy the intense whiteness of the sun today. It's compared to yesterday when there was so little of that. Have a good day. Thanks for being back.